All right. Yeah, Diels-Alder is still here. Okay. One of the other things we need to talk about are these bridged bicyclic compounds. I looked at these and I wanted to scream, but they're actually not that complicated. And I'm going to show you exactly why. Okay, first of all, some of the theory behind this is that when we're doing our Diels-Alders, really everything's been looking like this. It's in a cis conformation. That's what we want. Okay, this is good for Diels-Alder. This is going to react. If something is locked in a trans conformation like this, it's not going to go to undergo this reaction, as you can see here. Okay, but here's the thing. Even though this is cis, it's not locked. Well, can you make something that's cis that is locked? Well, you can, and they give you an example of something that's locked like this. So we're used to looking at part of this. We're used to looking at this in all of our reactions so far, but what if we lock it? That's kind of interesting. So let's take a look at this. Try to draw these a little nicer. That's my little pentagon there. And let's number our conjugated system like we always do. Now, still, we know that we're going to end up with a product that has a double bond between 2 and 3. All right, let's keep that in mind. Here's the crazy thing that happens, because what are we reacting it with? We're reacting with this. Remember, this is our conjugated diene. Also remember that it is symmetric. It is symmetrical, but I don't think for this that really matters. And what are we reacting it with? Well, we have, let's put our approach here, CH2, C, and then we have this, what's that, an ether group, methyl oxide, whatever. Oh, it's a CO2. Who cares? It's this. Okay, that's what's approaching. Now, if this was just a normal, if this was just our normal deal, right? We do our ring around the rosy with our 3 brothers. And that's our answer. But that's not the deal, because what happened to our pentagon? There was a pentagon blocking that from occurring. Here's the cool thing. Just pull that up. Just pull it up. Well, what do I mean by that? I mean literally take this carbon and pull it above so that our double bond can approach. And the way that that looks on a piece of paper is something like that. All right, and I know that looks kind of crazy. That's literally the answer, though. It's that easy. Sort of, because they use this weird type of chair configuration. Sorry, I dropped my pen. They use this weird type of chair conformation. And we can still number this just like we did, okay? We have a 1, 2, and a 3, and a 4. Remember, our double bond is sitting between our 2 and our 3. So this is a carbon. This is a carbon. This is also a carbon. This is 1. This is 4. And what comes after 4, it's that carbon that we pulled up. This is 5. That's up here, okay? Okay. But they draw this in kind of an interesting way. The way that they draw this is with, I think, the double bond going down. The way they draw this is like this. That's our 2, that's our 3. This goes this way. And then it's just like a weird rectangle. Okay? And then our bicycle sits up here. Okay? Let me number it. 1, 2, 3, 4, 5. Okay? And how many carbons did we add? We added A. We added B. And they're still here. We added A. We added B. And what was attached to B? Well, this CO2CH3. But because we're sort of in like a chair conformation type of deal here, we need to choose axial or equatorial. Okay, does it matter? Well, you could put it axial, or you could put it equatorial up. Here's the thing. When it's pointing away, when it's being exiled from the double bond, it's called an exoproduct. When it's not pointing away from the double bond, even though this is pointing down, it's not in the away direction, this is the endo product. Okay? What do we got here? So anytime when their diene is a cyclic compound, like it is here, the product of a Diels-Alder reaction with our dienophile is a bridged bicyclic compound. I drew it in 2 different ways. This is carbon B. I drew it in 2 different ways. That's the way that this works. The exo-endo thing, the endo product is formed faster when the dienophile has a substitute with pi electrons. Dienophile has a substituent with pi electrons. I guess because there's some double bond action happening here. So the endo is going to be formed, favored, and in this case, it is. Yep, the endo, which is the one that is not pointing away, not pointing towards, but also not pointing away, is endo. That's going to be the one that is preferred here. Don't ask me why. I really don't know, but just know that endo is favored. Some studies about that, whatever. But that's bicyclic compounds.